this video, we're going to determine the length and width of a rectangular yard in which the area is maximized when we have 100 meters of fencing. The first step that we take to solve this problem is to identify the objective, any constraints that we must abide by, and the endogenous variables. So our objective is to maximize the area, and since we know that we're dealing with a rectangular yard, the area will be equal to length times width. Now, the one constraint that we have to abide by is that we have 100 meters of fencing to deal with. Now, whenever you see a problem involving a shape and fencing, the fencing is going to correspond to the perimeter of that shape. And we know that the perimeter of a rectangle is equal to 2 times the length plus 2 times the width. So this implies that the constraint will be 100 is equal to 2L plus 2W. Now, the endogenous variables for this problem are the variables, and actually any problem, they're the variables that we get to choose in order to maximize or minimize our objective. So the variables that we choose in this problem are length and width. And for instance, the perimeter would be an exogenous variable because that is something that is given to us that we're not able to choose. So once again, the endogenous variables are length and width because that's what we're choosing. Now, to summarize this constrained optimization problem, I'm just going to put it in standard notation. So we're going to write max, and then we've got the objective, which is length times width, such that 2L plus 2W is equal to 100. And then we're going to put the endogenous variables. So we're going to maximize the objective by choosing the endogenous variables length and width, subject to that the perimeter of the rectangle is equal to 100. The next step in solving this problem is to set up the Lagrangian, which is just going to be equal to the objective function plus a Lagrange multiplier multiplied by our constraint set equal to 0. So formally writing this out, we get that the Lagrangian is equal to length times width plus the Lagrange multiplier lambda multiplied by 100 minus 2L minus 2W. So what I did right here in the constraint part of the Lagrangian is I just took our perimeter constraint and moved the 2L and 2W over to the left-hand side. And when we do that, the constraint is equal to 0. So I just subbed that into the brackets in the Lagrangian. When I first started dealing with Lagrangians, I was always confused as to whether to put a positive or in front of the constraints or a negative, or if it mattered whether I wrote 100 minus 2L minus 2W or 2W plus 2L minus 100. As it turns out, when we're just trying to solve for the endogenous variables, it doesn't matter which way we put the signs because those signs are only going to affect the lambda value. And they affect the lambda value by just switching it from a positive to a negative depending on the signs that you choose. And since we're not actually trying to solve for lambda, we're trying to solve for the endogenous variables L and W, it really doesn't matter which signs we use. Now that we've set up our Lagrangian, we are going to have to take our first order conditions for this problem. Now the first order conditions are going to give us a set of equations, and then we're going to use that system of equations to solve for the length and width that maximize the area of our rectangle. Now we're going to have to take a first order condition for each endogenous variable L and W and each Lagrange multiplier lambda. And keep in mind, there's going to be, with how many constraints that we have in this particular problem, there's going to be one Lagrange multiplier. So since we're dealing with one constraint, the perimeter constraint, we're going to have one Lagrange multiplier. Now, the first order conditions are going to be such that we take the derivative of the Lagrangian with respect to each endogenous variable, so the derivative of the Lagrangian with respect to L, the derivative of the Lagrangian with respect to W, and the derivative of the Lagrangian with respect to lambda. And we're going to have to set each of those derivatives equal to 0. Just to briefly overview why we set each first order condition equal to 0, keep in mind that the derivative is just the rate that a particular function changes as you change another variable. So if you refer up to the top right hand corner, I'm going to draw a 2-coordinate grid with an endogenous variable L and the Lagrange function on the y-axis. So when we take the derivative of the Lagrangian with respect to L, we can see that we're just getting the rate of change, or the rate that the Lagrangian changes as we change L. And since the derivative is equal to the rate of change, right, we know that the derivative is going to be the slope of the tangent line to this particular function. Now, when the slope is equal to 0, right, the line is going to correspond to the optimized value of that particular function. Then what we're going to do is we're going to solve for the L, and that's going to give us the L that maximizes the Lagrange function and in turn the objective function. And by setting the derivative equal to 0 for each endogenous variable and the Lagrange multiplier, we are going to effectively optimize our objective. Now, taking the derivative of the Lagrangian with respect to L and setting that equal to 0, we end up getting that W minus 2 lambda is equal to 0. And then this simplifies to lambda is equal to W divided by 2. Taking the derivative of the Lagrangian with respect to W, we end up getting that L minus 2 lambda is equal to 0, which simplifies to lambda is equal to L divided by 2. And taking the derivative of the Lagrangian with respect to the Lagrange multiplier, we end up getting our original constraint, that is 100 is equal to 2L plus 2W. Now, when taking the derivative of the Lagrangian with respect to the endogenous variables, when I simplified these equations, I simply isolated lambda to one side of the equation. And this is going to make substitution quite easy. So we can see that lambda is equal to W divided by 2, and that lambda is equal to L divided by 2. So this implies that W divided by 2 is equal to L divided by 2, which further implies that W is equal to L. Now, using this condition that the width is going to be equal to the length, we can sub this in to our original constraint to get that 100 is equal to 2, for instance, L plus 2W, which, since we know that W is equal to L, we can sub L into this equation. And then solving for L, we get that L is equal to 25, which implies that width is equal to 25 as well. So now we've got that the length and width that maximize the area of this rectangle are both going to be equal to 25. And with this information, we can actually solve for the area as well. So we know that the area is going to be equal to 25 squared, which is just 625 meters squared. Thanks for tuning into this video. I hope you found it helpful. If you did, please like and subscribe, and check out my other videos to see more problem-solving content.